Let's have a look at some new physics. The effect we're about to observe is that a changing magnetic flux, d phi dt, through an open surface bounded by a wire loop induces a current in that loop, an induced current. And the direction of that current is conventionally given by a rule of thumb known as Lenz's law. Okay, so here's the phenomenon. Suppose we have a wire loop with no battery or power supply or anything in it, just a conducting loop of wire and a bar magnet. You would find that if you pointed the north end of the magnet towards the loop and moved the magnet towards the loop, a current would start to spontaneously run in this direction around that loop for as long as you were moving the magnet in towards that loop. If you were to change the rate at which you moved that magnet in, so grab that bar magnet and push it in with a greater speed, the current induced in that loop would still be in this direction, but it would be a much greater current. So the induced current we're finding is proportional in its size to the rate at which the magnetic flux through the loop is changing. Okay, what if we take that magnet and pull it away from the loop instead? If we pulled it away from the loop to the right, we would find that a current in this direction was induced through that loop. Okay, so the current that we get depends in its size on the rate at which the magnetic flux through the loop is changing. And it also depends in its direction on the direction of that magnetic flux. Or rather, it depends in its direction on how the magnetic flux is changing. Is the magnetic flux increasing or decreasing? Other examples. Suppose we flipped the magnet, so the south pole of the magnet was facing our wire. Now we're getting flux in a different direction through that loop. And as you pulled the magnet away to the right, you would see we would get an induced current in this direction. So what we're going to try to figure out here is how to predict the direction and size of the induced current that appears in response to a changing magnetic flux. A couple more examples. Suppose we took our bar magnet and held the magnet still, but instead grabbed our wire loop and pushed our wire loop towards the magnet. So moving the whole loop to the right. That's going to be changing the flux through the loop, and if we did that, we would find that current got induced in this direction. Lastly, if we held both the loop and the bar magnet still, we would see no current in the loop. So a magnetic flux is insufficient to produce a current. There is a magnetic flux through the loop here, but no current. That flux has to be changing for the current to be induced. So how do we explain this sort of thing? We'll be able to understand it if we recall that current induced in the loop, that current is going to be generating a secondary magnetic field of its own. So a current loop represents a magnetic dipole. We can use our right-hand rule. Imagine grabbing the near side of that wire here for the going along with the left-hand picture. Grab the near side of the wire, thumb in the direction of that current going this way, and our fingertips would curl around the wire, showing that we would get magnetic field lines pointing up out of that loop and indicating a north pole here above the loop. There'd be a south pole down here below the loop. Likewise, if we reverse the direction of that current, then we'd be creating a magnetic dipole with the south pole up here and a north pole down below. So that's the key. These induced currents are going to be generating their own magnetic fields. We'll call those the secondary magnetic fields or the induced magnetic fields from the induced currents. So here's the thrust of all this. The phenomena we're looking at, the new physics we're seeing, is a kind of electromagnetic inertia that appears in nature. We couldn't have predicted this from any of our previous laws. This is something new. It's kind of a system's resistance to a change in magnetic flux, an inherent resistance to a change in flux that exists in nature. This inertia is always a resistance to a change in something. Here we're resisting a change in magnetic flux. Okay, and Lenz's law tells us the direction of the current that will be induced in response to a changing magnetic flux. A changing magnetic flux will induce a current that attempts to, here's the big idea, maintain the original magnetic flux. Let's apply that to these examples above, see if we understand what Lenz's law is saying. Okay, suppose that for each of these open surfaces bounded by the loops, we're going to define a front side and a back side to that open surface. So in all cases, let's have the front side be the side on the right here. So our little surface area vectors will point to the right in all six of these loops. Okay, so our dAs are always to the right. So any magnetic flux to the left we'll say is an inward flux, and flux to the right we'll say is an outward flux. So in this first example, with the North Pole here shooting magnetic field lines to the left, we have B field opposing the dA. So B dot dA would be negative when computing magnetic flux. So our magnetic flux would be negative. We would call that flux inward into the surface. So we have here an inward magnetic flux, and as the magnet moves closer to the loop, that flux is going to be getting stronger because the B field here, where the field lines are close together, is stronger than the B field over here, where the B field lines are spread apart. So stronger B field, weaker B field. As the magnet moves in, the stronger B field gets closer to the surface, so we're strengthening the flux coming through that surface. According to Lenz's law, the system will respond by attempting to oppose that changing magnetic flux. The system will respond by trying to maintain the flux as it was, maintain inward flux. Okay, so if there was some inward flux, but that flux is getting stronger, the system is going to respond by trying to create some magnetic field pointing outward, which will reduce the inward magnetic flux. So in other words, since there was an inward flux getting stronger, the system needs to produce some outward flux to oppose the strengthening inward flux. And that happens by causing a current to run in this direction around that loop, generating a secondary induced magnetic field pointing in that direction. So our induced B will point outwards, maintaining the original flux. We would see the same thing in this example here. We have a magnetic flux that is inward and getting stronger as the magnet gets closer. So we need outward magnetic field to oppose that changing magnetic flux. And we get a magnetic field this way to the right by having a current run in that direction around our loop. So there is our secondary induced magnetic field opposing that change in flux. Same thing in, let's see, this example. No, not there. Down here. Here, the magnetic flux was inward, but since the loop was getting closer to the magnet, that flux was getting stronger. Inward flux getting stronger, so an outward B is needed to maintain the original flux. So we'll have current running in this direction to produce that outward B. Okay, what about this example right here? In this case, we have an inward magnetic flux, but since the magnet is moving away, the flux is getting weaker. The strong field here is getting further away, and there's more of this weak field coming into the plane of the loop. So we have an inward flux that's getting weaker. We need to add more inward flux to maintain it at what it was. So inward magnetic field is needed to maintain the flux. Before I was saying oppose the rate of change of flux. Another way of expressing that would be to maintain the original flux. So inward B is needed to maintain that flux. We can get an inward B, a leftward B, by having current run in this direction around the loop, generating a secondary induced magnetic field pointing to the left. That flux will attempt to maintain the flux at what it was, try and replace the weakening flux that we're getting as this B field is drawn to the right. Let's see, last example here. Here, where the south pole is pointing towards our loop instead. In this case, the magnetic flux is pointing outwards towards that south pole, so you've got an outward flux, but if that magnet is moving away, then the strong field here is moving away, and the weak field here is moving into the plane of the loop. So we have an outward flux that's getting weaker as the magnet gets further away. Therefore, we need to add more outward flux to maintain the flux at what it was. It's getting weaker, so we have to replace it. We need more outward B to maintain the flux. How do we get outward B? How do we get B to the right? Well, by having current run this way around the loop, generating a secondary or induced B field that way. There we go. So in all those cases, we're seeing how the changing flux induces a current. That current will create a secondary magnetic field, an induced magnetic field, in such a direction as to maintain the original flux.